So this video is going to cover moment diagrams with superposition. To start with, we have a simply supported beam, we have a pin at A, we have a roller at B. We have two linearly distributed loads, both of which have a maximum 3 kips per linear foot, both of which are acting across 5 feet of this beam. So to start with, we probably want to find our reaction forces, AY and BY. Now we don't have to find both of them because, of course, to do superposition, we're going to lock one end of this beam. So what we're going to do is we're going to fix our beam at A when we're doing this. So I need to find BY. In order to do that, I'm going to start by summing the moments about A. So if I sum the moments about A and set it equal to 0, I'm going to take counterclockwise to be positive, though it really doesn't matter. It's just going to tell you the direction of your arrows. So to start with, for the moment, I'm going to start on the left side here, and we have an area of 1/2 times the base of 5 feet, times the height of 3 kips per linear foot, and the distance from its centroid, which is about 2/3 of the triangle, over 2A, is going to be 1/3 times that base of 5 feet. Plus, this is going to be going in this direction. That is not the direction that we assumed to be positive, so that's going to be a negative number. Now we also have the one on the right. He's going to be going this direction, and that's also going to be a negative number. So we have minus, again, 1/2 the base of 5 feet times the height of 3 kips per linear foot, times, again, the distance from his centroid, which is way out here. His centroid is 2/3 of 5. So 2/3 of 5 feet plus the 5 feet originally. So that's both of our linearly distributed loads. Then we also have BY, and BY is going to be causing positive rotation for once. So we have plus BY times his distance of 10 feet. Set it all equal to 0. You have two negative numbers and BY, so when you move the negatives to the other side, BY will be positive. So you multiply all of those numbers, all of these numbers up here, all together, and then we're going to divide by 10. So we're going to find that BY is equal to 7.5 kips going up. So great. We have a point load, and we have two linearly distributed loads. So if we fix it at A, we're going to be taking our moment diagram. Over here at A, we've got positive and negative. Here we have A, and we have B on the other end. So to start with, we need to start figuring out how we're going to get the diagram shown above, right? Because we need to figure out how to break all of our loads down into things that are effectively cantilevered at A. Now, this first one, the one here on the left, the 3 kips per linear foot, it is effectively already cantilevered at A, so that's really nice. So what we can do actually is just put him in, and he's just going to be, we'll color him, say, yellow. He's going to be coming from the 5 feet, so right there in the center. He is a downward force, and he's going to start here at the tip of that downward force, and he's going to go back at a 3rd degree. So that's a 3rd degree, and of course this is going to be negative WL squared over 6. W being 3 kips per linear foot, L being 5 feet squared divided by 6, we are going to get a negative we're going to get a negative 12.5. So we'll clean this guy up just a little bit over here. So we have negative 12.5. So he's the easy part. We also have our point load, by. That's nice and dandy. So by is going to be in our green color. He's going to start from 0 over here, and his direction is positive, as you can see here. So he's going to be going up. So from this point, he is going to go up all the way out to our fixed end, and his value is simply P times L. So 7.5 times a total distance of 10 feet, that's going to give us 75. Cool, so those are the easy ones. Now we need to figure out how to do this guy. How do we get that shape? So we want to try and kind of use similar shapes or easy shapes to kind of create this thing. So for example, on our beam, an easy shape is a uniformly distributed load, right? And we just want to keep this part of it. So if we wanted to keep this part of our entire thing, what we should probably do is have a triangle, right? So we'll have a triangle, that's easy, and he's got to go against this uniformly distributed load. But he's technically going all the way up here. So if we were to actually draw that out in a little bit better looking diagram, we have our positive arrows and we have our uniformly distributed. So that's all nice. That has managed to get rid of the top part, right? We have actually managed to get rid of only this part where they overlap. So we have a slight issue here, and that's that we still have this other piece down here. So how do we get rid of it? Well, we need to add that piece down here again to the top. So let's add that dude in. So if he's going up, we need to maybe make him go down. So there we go. Now we have the orange part canceling from where they overlap. We have the two pinks part canceling as we just now created what's up here. So this piece is going to cancel this piece down here. And again, our distributed load is canceling our uniformly distributed load. And we're left with the part we actually care about. So that's great. So now we have to draw these three shapes as loads. We need to turn those into our moment diagram. So we have two linearly distributed loads and one uniformly distributed load. And all of this only acts across our, I guess technically 10 feet. And this part right here is at 5 feet. So this gets a little bit fun. So not too bad, but what is the values for all of these shapes? Well, for starters, this total height here is 3 kips per linear foot, because that is the end value over here. So if that's 3 kips per linear foot for that part of the triangle, then this part of the triangle down here is also at 3 kips per linear foot. But 3 kips per linear foot plus 3 kips per linear foot puts us at a grand total of 6 kips per linear foot for the purple one. So again, we've got 3 kips per linear foot for the black one. We got 6 kips per linear foot for the purple one. And for our nice little magenta one, we also have 3 kips per linear foot. Now, if you just want to check and make sure, we can verify that based on our loading, we've got our triangle down here and our triangle up here. Those are equal and opposite. Great, those are canceling. Then we've got our rectangles right here canceling. That's great. And then we've got this triangle canceling out this triangle. So those two triangles canceling out. And we're left with the one and only golden glorious piece that we wanted the entire time. Huzzah! So we just need to put these onto our diagram. So we can start with the magenta one. So we have this little distributed load going down. Again, it's going to start from 5, and it's going to go down. And it's going to go actually at the exact same thing that we had before because he's the same exact shape. So we actually have a second one in here, also at 3 degrees, also at negative 12.5. That got a little bit squishy. So we have 2 curves at the same spot. Then we'll draw the black one in dark blue here. So for the dark blue one, that's going to be our uniformly distributed load. That'll be this guy. So he's 3 kips per linear foot, uniformly distributed. He's going to be going down. So we're starting at the end, and he's going to be going down. This is a 2nd degree curve. And he's going to be at W L squared over 2. Of course, he's negative because he's going down. So negative W, 3 kips per linear foot, times L squared, so L being 10 feet squared divided by 2, is going to put us at negative 150. Kind of a far way down. Then we have the purple one. Right, then he's a really big triangle going up. So he's going to be pushing us up. We're going to start at the pointy end, the small little pointy end over here. So we're going to start at the pointy end and we're going to go up. And since he's linear, he's going to be a cubic right now. So he's a cubic going all the way up to W L squared over 6. W is 6, 6 over 6 times L squared, so that's going to be at 100. And he again is a 3rd degree. Kind of forgot to label our one green curve. He was a 1 degree. So technically, that is our moment diagram using superposition. We have it going all the way up to 100 with the cubic. Then we have 75 with the linear. Then we have our 2 different ones, our negative 12.5 cubic and our negative 12.5 cubic, and then our negative 150 quadratic. So that, in a nutshell, is how to do moment diagrams using superposition.